electrophile, right? To be more specific, what do you need in an electrophile? Electrophile must have an empty orbital to accept electron. Right? To accept electron. Okay, there must be empty orbital to accept electron. Or sometimes it can also contain an atom that can leave with a pair of electrons. For example, SN1 and SN2 reaction. Right? To be more specific, those are alkyl halides. You notice that if you are talking about SN2 reactions, sometimes you have an X here. You notice that the nucleophile comes in, it attacks and it leaves. Right? So there are two scenarios that you can act as a electrophile. It's either you have a empty orbital or you contain an atom that can leave together with a pair of electrons. Right? So be clear with nucleophiles and electrophiles. Then the few factors here affecting electron availability of a bond. There are four factors here. Inductive, resonance effect. Probably inductive effect you have heard before. Resonance effect you may have heard before, but you don't know what it really talking about. Conjugative and hyperconjugative, which is just something like conjugation, which you should have introduced already in MO diagram. So for inductive effect first. Now what is inductive effect? Inductive effect is created because of what? Due to the presence of a more electronegative atom attached to one of the carbon atoms that leads to the bond polarization. So for example, right, you look at the picture here, is a chloroethane. We know that chlorine is highly electronegative, right? And then this carbon here that's labeled with 2, carbon 2, right? I mean, with a label number 2 there, you'll be partial positive. In fact, carbon 1 will also be partial positive. I hope you understand why I'm putting a big partial plus and a big partial plus and a small partial plus. Basically, I'm just telling you that the effect of polarizations gets bigger and bigger as it goes further and further away from the chlorine atom. That's inductive effect. It's mainly due to what? It's mainly due to electronegativity issues. Got it? That's inductive effect. So therefore, the ability of an atom or group of atoms to withdraw or donate electrons through a sigma bond is called inductive effect. You must have a sigma bond. And it's mainly due to electronegativity issue. Right? That's inductive effect. Then the next one, resonance on the next page. Resonance effect always results in a different distribution of electron density. There will be the case that there's no compared to Roman resonance. So in other words, electrons disperse over several atoms. Can you please change this word and call it delocalized? Because I think in H2 you all learn electrons delocalized, charge dispersed. Right? Electrons must delocalize over several atoms rather than to concentrate within a single atom. So for example, in the phenylamine, I don't think you have learned until nitrogen compound, right? For H2. I mean, right? I learned already. Oh. If you like this phenylamine, you should know that there's a lone pair. What is the hybridization of the nitrogen? Very quickly, you should be able to tell me from the paper that I've given to you just now. It is actually sp2. To be sp2, there will definitely be a p orbital. So therefore, if I draw it out at the side here, there's a p orbital on the end that's overlapping with the high electron cloud in the benzene ring. So what happened? The lone pair starts to delocalize. And if I were to draw in the resonance structures or resonance way, right, this pair of arrow comes down to form that double bond. And this pair of electrons in this double bond come to this carbon here. So now the negative charge, the extra electron is carried by the carbon here. Things don't stop there. Comes down. This pair of electrons comes here. pair of electrons come down, comes here. That's why you find that the negative charge starts to move around. That's what the question, what the paragraph above is trying to tell you. Electron density don't concentrate on one atom. It starts to spread around. It don't only stay in one atom, it starts to move around. Okay? That's what we call delocalization. Right? The opposite is called localization, which is just to stay in the atom, but now it's delocalized. Right? So that's how these four structures comes about. Now of course, if I were to draw another one, right, there's a pair of electrons here. If I draw it like that, comes down, this pair of electron goes up, it goes back to the first structure. Okay? It goes back to the first structure. So to conclude, based on what this resonance effect is talking about, basically just telling you lone pairs don't just stay on one atom, but start to delocalize over a number of atoms. All this can happen because of what? You notice that the red color picture that I drew, all this happens because there are p orbitals that are adjacent to each other. If there are no p orbitals adjacent to each other, delocalization cannot happen, right? So it must overlap, just like what I told you on Tuesday. Carbon 1, carbon 2 are overlapping now, but can carbon 2 and 3 also overlap? There's also a chance. So that's why I bring the pair electrons over to carbon 2 and 3, which is what I'm trying to show you here. Carbon 1 and 2, right? Then you notice that the pair electron comes down to 2 and 3. All this happens because of the p orbital. Okay? So it's only when you have p orbitals, then the electrons can delocalize. If not, you cannot delocalize. And they must be adjacent to each other. Okay? And it happens because, like what I said, the pi bonding. And you should know pi bonding can only be formed when you have p orbitals. Right? Then another possible effect, right, is conjugative effect, conjugation, which I think Mr. Chin should have mentioned to you in this MO diagram. Conjugation. Double bond, single bond, alternating each other. Those are called conjugation. So it's the same idea here. Conjugative effect. So there are various kinds of conjugative effect without any intervening atoms. What are intervening atoms? For example, if I draw it this way. There's no more conjugation. Why? Because you notice that the carbon right in the middle, this carbon here is in fact sp3. If it's sp3, there's no p orbital. There's no p orbital, while the rest of the alkene carbon has p orbital. Right? So therefore, this intervening atom I'm referring to is this carbon in the middle. So as long as there's no intervening atoms, as long as, again, the adjacent atoms have p orbitals, there could be conjugative effect. Okay? So this conjugative effect is useful because it is used to stabilize pi system. Right? It's used to stabilize the pi system. So you look at the two examples at the bottom. It can be conjugation like in benzene ring, or even the cyclo 1,3 butadiene. Not cyclo. Butyl 1,3-diene, this one. Right? Or even a benzene ring conjugation. It can also be cross conjugation, where you suddenly have a double bond right in the middle. So other examples would be, you can continue drawing on and on, right? No matter how long your carbon chain is, as long as your double bond, single bond alternate each other, right? There will be conjugation. You notice that all these carbons here have p orbitals, sp2 hybridized, adjacent to each other, conjugative effect can happen. Okay, destabilize it. Then the next one is hyperconjugative effect, which probably is new to most of you. What is hyperconjugation? It's more applicable if you are talking about things like the example, the picture here. There's a carbocation ion, which is trigonal planar. So this carbon here that I put a blue color dot, right, is actually sp2, trigonal planar. sp2, there's an unhybridized p orbital. But the neighboring carbon, where I put a red dot, you have to know that this is sp3, right? So this sp3 carbon with the CH group there is able to have a bit of this hyperconjugative effect to stabilize the carbocation ion, right? I mean, in H2 you always learn, alkyl group is able to stabilize carbocation, right? They are electron donating. So why are they electron donating? Then hyperconjugative effect. You notice that this is straight, but this one here, this CH bond, 109.5 degree. So if I were to look at it in terms of actual diagram, this p orbital is straight, but this CH bond is just slightly tilted. They are quite close, and there could be some overlap here. You notice that this arrow, little arrow here that I'm trying to tell you is, these pi electrons that were sharing between the carbon and hydrogen have some donating effect to this empty p orbital. That's how it stabilizes. So that's what we call hyperconjugation. And can you see that if I have more alkyl groups, more hyperconjugation, the more stable the carbocation is. Now it's only one alkyl group, primary carbocation. If I will put one more CH3 here, one more CH3 here, there will be more conjugative, hyperconjugative effect. The more stable will be the carbocation, right? So that's actually called hyperconjugation. And you notice this symbol here, beta. Only electrons in the bonds that are beta to the positive charge carbon. The beta is just basically referring to adjacent. In a lot of textbooks, it's called beta. It's just adjacent to the positive charge carbon. You can stabilize it. It's what we call hyperconjugation. Right? So I just repeat again. It's just because the carbocation p orbital straight, but the CH bond tilted a little, 109.5 degree. So they are quite close. There could be some overlap between the orbitals. That's why the shared pair electrons in the CH bonds are somewhat donated to the unhybridized p orbital. That's called hyperconjugation. Right, so these are a few couple of effects that you will come across along the way, inductive, resonance, conjugative, hyperconjugation. And I think these four effects here should be, yeah. Then the next page, factors affecting the rate of nucleophilic subreaction. You have to know the different rules here and how it affects rate of reaction. Okay, so just to summarize, there are four factors that I need to learn. The first one is the nature of the nucleophile, right? The nature of the nucleophile. So nucleophilicity refers to the ability of a nucleophile to donate electron pairs, and basicity refers to the ability of a base to donate electron pairs. Now you notice that this sentence here about nucleophilicity and basicity sounds a bit funny. How come we talk about nucleophile and then suddenly the lecturer says bases? Are they related to each other? Yes, they are, right? I thought base must accept H plus. Yeah, alright, you're not wrong. In other words, in this lecture, I'm going to tell you a nucleophile is a base. A base is a nucleophile. Okay? You put it down first. A nucleophile is a base. A base is a nucleophile. Now, of course, you will ask, are you talking crap? I'm not. How can a nucleophile be a base and a base be a nucleophile? Don't get me wrong. In fact, the definition was stated on the first page just now. If you have realized. The base I'm talking about here is a Lewis base. The base I'm talking about here is a Lewis base. I'm not talking about Bronsted base. Right? You have learned the three definitions of bases, acids and bases last year. Arrhenius, Bronsted, Lewis. And then you realize that along the way, throughout these 2 years, I've not been handling Lewis bases before. In fact, you are handling it, you are not realizing it only. Lewis base, Lewis acid is more applicable for organic. Right? So a Lewis base is a what? Lone pair donor. Lewis acid is lone pair acceptor. So you notice that all the mechanism that you are drawing, right, in fact, happen because of Lewis acid base theory. You are not realizing it only. So a nucleophile must donate a lone pair. So that's why a nucleophile is also a base. Got it? Right. So just take note, this base here is not the constant base. I'm talking about Lewis base here. And you'll notice that on the second paragraph here, I put there in bold, the nucleophilicity and basicity are both increased with increasing negative charge. I think it makes sense. You should be able to realize this. For example, in the first bullet point there, right? Nucleophilicity decreases with decreasing basicity. In other words, I'm telling you, basicity is proportional to nucleophilicity. They are proportional to each other. RO minus, OH minus. How come RO minus is a stronger nucleophile, right? I mean, comparing the trend, you notice that those with negative charge are the stronger bases. Those without negative charge will be the weaker bases. Lewis base, or you can put it this way: those with negative charge, strong nucleophile. Those with no negative charge will be weaker nucleophiles. But among the negative charge ones, R group electron donating, it donates electron to the O. It makes the lone pair here on the O more available to donate away. So that's why the RO minus will be your strongest nucleophile. Right? Then followed by OH minus. I hope you know what it is. C6H5O minus. Phenoxide. Phenoxide is not a very strong base. Right? It's not a very strong base. Or should I say not a very strong nucleophile. Why is that so? It's all going back to your H2 basics. Benzene ring. O minus, p orbitals are all overlapping. Lone pair electrons delocalize into the ring. Right? It makes the phenoxide not a very good nucleophile. Right? Followed by carboxylate, alcohol, and then water. Those without a charge will be a poorer nucleophile. But you have to be very careful. It says here, nucleophilicity is important. Something that you need to consider because it affects SN2 reaction. But it is also affected by steric effect. Nucleophilicity is also affected by steric effect. You take note of these two examples that was given to you, that was printed on the notes. Right? So previously, we have been agreeing nucleophilicity is proportional to basicity. But there's only one exception. This is the exception here. Right? This exception here, be very careful. For example, the structure on the left-hand side. You notice that there are 3 R groups, 3 alkyl groups. 3 alkyl groups will definitely make the lone pair electrons on the O highly available. It's definitely going to intensify the negative charge. But it's not a very good nucleophile. Right? It's not a good nucleophile. Why? Because this big group here actually kind of block the approach in SN2 reaction. For example, if I draw it here, let's say it is an SN2 reaction. These are halogen, partial plus, partial minus. Now we know that a nucleophile, let's say you have a lot of R groups. You need to approach the carbon in order to suck out the X. But having so many R groups here, big R groups, it makes it very difficult for the nucleophile to even approach the carbon center. Right? So even if it's a strong base, it can be a poor nucleophile also. So this is the exception. Right? So this is one exception. Strong base, but poor nucleophile. Compared to the one on the right, right? It's a weaker base, but it's a strong nucleophile. Okay? It's a strong nucleophile. And it can be observed from the Ka values and Kb values. So you notice that the first structure on the left, right, tertiary butoxide, is a hindered base. It's a poor nucleophile. Tertiary butoxide is actually the conjugate base of the weak acid tertiary butanol. So the pKa value was given as 18. The pKb value will be given as -4. Right? pKa plus pKb equals to 14. Right? So if we are talking about ethoxide coming from ethanol, the pKa was 16, the pKb will be equals to -2. Right? So you can see that. How come I say tertiary butoxide is a stronger base? You just observe the pKb value will do what? The lower the pKb, the stronger the base. The higher the pKb, the weaker the base. Right? So that's the reason why I said tertiary butoxide is a stronger base, but it's a poor nucleophile. So it contradicts to what we have agreed just now. Nucleophilicity proportional to basicity. This is only one exception. But in general, most of the time is basicity and nucleophilicity are parallel to each other. It can be also be nucleophilicity can also be affected by electronegativity. Right? So for example, in this case here, you notice that the 3 or 4 on the left, just observe the carbon, nitrogen, oxygen, and fluorine. There's an increase in electronegativity. Okay. Well, talking about electronegativity and nucleophilicity, whatever things I want to say is actually mentioned in this paragraph here. It take a while to read through the paragraph. Why I say nucleophilicity decreases with increasing electronegativity. Okay, so in conclusion, is what I've written there on the left hand side. If you have higher electronegativity, just to get it this way, the lone pair electrons will be more tightly held on by the nucleus. It doesn't want to donate, that's why it's a poor nucleophile. Alright? Of course, as it goes down the group, comparing sulfur and oxygen, you also realize that sulfur is a better nucleophile compared to oxygen. So like what the explanation here says, if it's further away from nucleus, it's less tightly held onto the nucleus. Don't forget there's still shielding effect. It's easier to donate the valence electrons. Right? So that's why they are stronger nucleophile as well. Okay? So electronegativity affects nucleophilicity. And the last one I already mentioned, normally for negative charge nucleophiles, right? They are usually the stronger nucleophiles compared to low charge. And the last sentence there, it says that a base is a stronger nucleophile than its conjugate acid. Well, the base will be a stronger nucleophile than its conjugate acid. Yeah. Any questions until here? And there's one more factor on the next page which you seldom see. Right? Nucleophilicity of a given nucleophilic center increases by attached heteroatoms. For example, normally for OH minus, if I attach another OH at the side, it makes it a stronger nucleophile also by looking at the trend. Right? So that's what is being observed. But we seldom see this in exam. Right? There are two more factors that can affect nucleophilicity, which I will share with you in the extension topic. But I can tell you now, you may want to put it in. Nucleophilicity decrease with the localization of lone pair of electrons. I think it makes sense because, for instance, in oxide, you notice that the lone pair electrons was delocalized. Right? So if you have more delocalization of the lone pair electrons, then you find that the nucleophilicity will increase. The last factor that can affect nucleophilicity is hybridization. Notice that the two nitrogens there, one of them is sp3, the other one is sp2. Okay. So normally those that is on sp3 will be a stronger nucleophile. So of course, why is that the case? I believe you have heard about this before. S character issue. sp3 25% S character, sp2 will be 33% S character. So the higher the S character, you notice that S orbital is closer to a nucleus compared to, is more strongly attracted to a nucleus. So if you have higher percentage of S character, the lone pair electrons will be more tightly held on to a nucleus also, less likely to donate. So that's why sp2, the lone pair, if it's on the sp2 orbital, it is less likely to donate away. Hybridization is affecting nucleophilicity. Yeah, so these are two other factors which will be discussed later on. But I just want to share with you now. In the last chapter now. Okay? So first factor that you have to learn the nature of the nucleophiles. Nature of living group is the next one. The best living